This video is on the Ekman pumping velocity. The Ekman pumping velocity is a vertical velocity. It's at the base of the surface Ekman layer. We symbolize it as WE. If it's positive, then that's upwelling. There's water coming into the surface Ekman layer from below. And if it's negative, then it's downwelling and there's water being removed from the Ekman layer. Our first step in quantifying the Ekman pumping velocity is looking at the incompressible continuity equation, du dx plus dv dy plus dw dz equals 0. And we're going to integrate this vertically. For this vertical integral, we're going from z equals negative he, the base of the Ekman layer, up to z equals 0 at the surface. The first two terms, I've just written them as those integrals, and I haven't done anything with them yet. And the last term, the integral of dw dz with respect to z, is w at the surface, where z equals 0, minus w at the base of the Ekman layer. This is going to be our we, but right now I've got it written as w at z equals negative he. And this whole thing still equals 0. Now we've brought the ddx and the ddy outside the vertical integrals. I can do this by applying the Leibniz integration rule. To do this, you can look into it, but I had to assume that u and v are approximately 0 at the base of the Ekman layer, where it's z equals negative he. And then for the w term, what I've said now is the vertical velocity at the surface is 0. That means the surface isn't moving over time. And I've replaced the w at z equals negative he with our we, which is our Ekman pumping velocity. And that's all equals 0. Now I can rewrite the equation so that we is alone on the left-hand side, and inside the ddx and ddy, I've written the expressions as u bar, the depth average velocity in the Ekman layer, times he, and v bar times he. But then I also have this extra information. I know from the momentum balance that the depth average Ekman velocity is in the x direction, u bar equals tau sy, the wind stress, in the y direction, divided by rho f he, and v bar, the Ekman velocity in the y direction, equals negative the wind stress in the x direction, tau sx, divided by rho f he. And the rho, that's just a density that we use. It can be a constant density. We don't have to worry about its variations here. Here we just simply substitute in the expressions for u bar and v bar, and we have the derivatives of wind stress components over rho f. Since we don't have to worry about the density variations, we can bring that right outside the derivative, and now we have we equals 1 over rho times the quantity ddx of tau sy over f minus ddy over tau sx over f. Notice the mixture of the derivatives x with the y component, the derivative y with the x component of the wind stress. This could be our stopping point, an equation that we work with, but let's introduce some more notation. The wind stress vector can be written as tau s with that arrow over it equals tau sx I hat plus tau sy j hat, where I and j are unit vectors in the x and y directions. The other notation is the curl operator. It's ddx of the y component of a vector minus ddy of an x component, and that's what we have here. So with that notation, the Ekman pumping velocity we equals 1 over rho, the curl of the wind stress vector divided by f. And that's how you often see it, this curl of tau s over f. And that's a very important quantity for oceanography because it allows you to say where upwelling and downwelling are happening in these Ekman situations.